Space exploration and high-intensity telescopes have allowed us to learn about the planets of our solar system. Which planet is the largest, and what do we know about its composition and activity? The inner planets, known as the terrestrial planets, are nearest to the Sun and made up of rocks and metals. Earth is the only one fit for life. Closest to the Sun, Mercury serves as a dartboard for galactic debris drawn by the Sun's gravity. Its pitted surface roasts hot and dry. Hotter still, Venus boils away under a blanket of carbon dioxide. Infrared radiation can't escape the planet's surface. The only landing craft to reach this planet melted. Mars, with its familiar terrain, tempts us to search for life. Surely, rivers flowed in these ancient valleys. And volcanic eruptions must once have breathed fire here. Mountains on Mars dwarf Everest, and polar ice caps hold water just like our own. What happened here and when? Occasionally, bits of Mars fall to Earth with further evidence that life may have existed on the red planet. Meteors holding earthly minerals and the fossilized remains of what might be microbial life kindle scientific curiosity. But life as we know it cannot possibly exist on the giant planets Saturn, Jupiter, Uranus, and Neptune, made up largely of liquids and gas. Jupiter, the largest of the four, could swallow 1,300 Earths, the rest of our solar system's planets and moons, and still boast room for more. Still, Jupiter has no solid ground. It's a seething mass of gas and weather. Jupiter's storms may rage for lifetimes. The red spot on the planet's southern hemisphere is a tempest big enough to hold 2 Earths, and it was first observed over 300 years ago. Though no explorer will ever walk on Jupiter, the planet's not beyond our exploration. In 1995, the Galileo spacecraft looked into the planet's stormy atmosphere. For 57 minutes, the probe relayed information about Jupiter's gaseous layers, which proved drier, windier, and thinner than anyone on Earth had guessed. Then, the probe vaporized. And then there's Pluto. Tiny by comparison to its 4 neighbors, Pluto has an irregular orbit. No spacecraft has traveled to Pluto, and the world's best telescopes are required to see it well. It's still keeping secrets.
Okay guys, we're going to talk today about some of the objects in our solar system. And mostly this will be about planets. So let's just take a look at the 2 broad classifications of planets. The first group are the terrestrial planets, terra firma. So these are solid, rocky planets. Sometimes they're known as the rocky midges because they are kind of midgets in comparison to the other planets out there, the other outer planets. So these are the inner planets, Mercury, Venus, Earth, and Mars, and they are small and rocky. The outer planets, also called the Jovian planets, are Jupiter, Saturn, Uranus, and Neptune. And these things are humongous gas giants, so they're very different than the inner terrestrial planets. Pluto, which we'll probably talk a little bit about later, no longer fits into either the Jovian or the terrestrial category. So we consider Pluto now a dwarf planet. It's been dropped from the list of planets. So when I learned the planets when I was in school, I learned, of course, Pluto as the last planet, and that is no longer the case. We have demoted Pluto, but that's not necessarily a bad thing. Let's dive in here, and here's a quick overview of where the planets are located. We've got in there closest to the Sun, Mercury, Venus, Earth, then Mars. There's a jump there there's an asteroid belt between Mars and Jupiter, essentially where another planet should have formed, except for the fact that Jupiter is so big that it disturbed the orbits of all the material in there between Mars and itself and caused it to not be able to coalesce into a planet. So there's a big gap in there, and there's asteroids. From Jupiter, we go to Jupiter, Saturn, Uranus, Neptune, and then finally Pluto way out there. The Kuiper Belt is the region where comets come from, way on the far outer part there. This is the disk portion of our solar system. Solar because our sun's name is actually Sol. So there you have it. Let's move along here. The most obvious difference between the inner and the outer planets is their size, but they also differ considerably in how dense they are and what they're made up of. Also in their rate of rotation and how long it takes them to go around the sun. There's a lot of differences between the planets. Let's glance here in particular at the relative masses and the diameters of the planets. If you look there, kind of over towards the right a little bit, the diameters, I know there's been a lot in the news and a lot of talk about building a colony on Mars someday, but take a look at Mars compared to Earth and compared to Venus. Venus is actually much more our twin than Mars is in any respect to size and mass. Mars is considerably smaller than the Earth. It's also considerably less massive, 0.1 Earth masses. So that's considerably less. Gravity on Mars would be a lot less than Earth. Gravity on Venus, in comparison, would be much more similar to that of Earth. The only problem is that Venus is kind of a hellish landscape, and there's no possibility we could ever live on Venus. There is a possibility we could live on Mars, but we'd have to deal with some issues in terms of there not being much of an atmosphere, there not being plate tectonics, and there not being protection from solar radiation like there is on Earth, and of course the lower gravity would be kind of strange. We could easily dunk basketballs for those of us that can't currently. So let's kind of move along here. Let's look at the differences between some of the planets in terms of what makes them up. The substances that make up planets could kind of be divided into three groups. We have gases, we have rocks, and we have ices. Anything can be an ice that might exist as a liquid at Earth's surface temperatures and pressures. It could be frozen somewhere else. So it doesn't have to be water. We could talk about frozen methane. We can talk about frozen carbon dioxide. Lots of things can be frozen as ices. The Jovian planets, those outer planets, have really thick atmospheres. They're mostly hydrogen, helium, methane, ammonia. It's not surprising that they're mostly hydrogen and helium because that's what our sun is made up of. They're composed of the gases that didn't make up our sun. They got left in the outer part of the solar system. The terrestrial planets, in comparison, have very, very tiny atmospheres. So compared to the Jovian planets that are basically all atmosphere, Earth, Venus, Mars, Mercury, they have very, very tiny atmospheres. Looking at the scale of the planets, you notice that the rocky midges in there, Mercury, Venus, Earth, and Mars, are tiny, tiny, tiny compared to the Sun, compared to Jupiter. Jupiter is a monster. Saturn's not too far behind it, and as well as Uranus and Neptune are also quite large compared to the inner planets. Jupiter itself is kind of like a little miniature solar system in and of itself. It's not nearly big enough to become a star, but it is basically composed of the same material that our sun is composed of. Had it gotten that big, it could have been a second star. The way that our solar system formed is understood through what we call the Nebular Theory, or the Nebular Hypothesis. It's really more of a theory. A nebula is a cloud of gas and dust in space, and according to our best understanding, what is known as nebular theory, is that the sun, the planets all formed at approximately the same time, about 4.6 billion years ago, from a rotating, collapsing disk of dust and gases. Where did the dust and gases come from? Well, it's part of what makes up our galaxy, the Milky Way. So our sun is just one star among hundreds of billions of stars that make up our galaxy. We have, each of those stars probably has planets around it. We found many, many exoplanets at this point, planets external to our own solar system. So where did the gas come from, the dust? Part of that is from the original Big Bang, which we haven't talked about yet. But another part of it, a bigger part of it for us, is formed from the deaths of at least 2 other stars that happened to be nearby. Nobody was around to see this happen. This is billions and billions of years ago. And that material makes up our sun and makes up our planets. That's the reason we have things here like carbon that life can be made out of. That stuff came from the deaths of other stars. But we'll get to that later. As the solar system was forming, things began to accrete, to clump together because of collisions. Some collisions busted things apart, some collisions knocked things around, other collisions coalesced matter to form larger and larger things that eventually we started to call planetesimals. It's basically a baby planet. It's big enough that it's starting to become rounded, okay, by its own gravity. So these things get bigger and bigger and bigger, and eventually become planets, which round themselves through their own gravitational forces. If you ever wondered why planets are round or spherical, it's because all of the forces of gravity are pulling in towards the center, and that makes that big thing a ball. So here's a picture of a big nebula, gas and dust, collapsing, starting to rotate. Our sun is there forming in the center. All of the leftovers are basically what makes up the rest of the planets and the rest of the solar system. So looking at compositions considering distance to the sun, don't get confused by this graph, but it's super easy to understand. The idea is that the rocky planets are close to the sun. That's not an accident, and we think that that probably happens this way in virtually every other star system because of the fact that the sun is hot. Stars are hot. So being near them precludes or keeps gases from existing on those planets and as well as ices. So think about Mercury, Venus, Earth, and Mars. They don't have a lot of those gases that are in the outer solar system because they were too hot. They were boiled away. They were boiled right off the planets and pushed into the outer solar system. The same thing goes for the ices. They sublimated, they evaporated, they became gas, and they were driven away into the outer solar system where it's cooler and they can exist as an ice. So looking at Jupiter, Saturn, Uranus, Neptune, Pluto, those things are very icy, they're very gassy. That's because that stuff can exist there. All the heavy stuff, by the way, like the iron and the aluminum oxide, the tungsten, the nickel, all that stuff's on the inner solar system. Looking at the planets together, let's start and we'll go through them here. The terrestrial planets, starting with Mercury, closest to the sun. It's hardly larger than Earth's moon. It's pretty tiny. It's very cratered. Looks an awful lot like the moon in many respects. There's big smooth terrains that resemble the mare on the moon's surface. We'll talk about those here in a second. Otherwise known as the seas. They don't have water in them, right? They do not have water in them. The surface temperatures on Mercury are crazy hot, and they're very extreme. On the side that's facing the sun, it's very, very hot. On the other side, it's very cold. So it's got some very extreme temperatures. Chances for surviving on Mercury, 0. Let's move on to Venus. Venus is sometimes known as the veiled planet. It's also called our twin. Because of the fact that it's roughly the same size as Earth. If you could stand on Venus, it would feel about the same in terms of gravity. However, the atmosphere would be crushing. It's 97% carbon dioxide. It has a very, very thick atmosphere, which causes the greenhouse effect to be incredibly, incredibly effective. That takes the temperatures to a soaring 475 degrees Celsius. That is really hot. Um, Humans could not ever exist on the surface of Venus. It's just not going to happen. It's not a place we even consider spending any time. We probably could never even put a person there, even for any short amount of time. It's not some place we could land. Um, there have been probes that have made it to the surface of Venus. They did not last long. We've got maybe a couple pictures back from the surface before the probes were destroyed by the atmosphere and the temperature. It's a pretty hostile environment, but Venus serves as a humongous warning to us in terms of climate change. It is a huge example of what happens when you have a runaway greenhouse effect. This is where we get the idea of being concerned about Earth's greenhouse gases. All we need to do is look at one of our close neighbors here, Venus, to see what happens when you get too much carbon dioxide in your atmosphere. Now, we're nowhere near 97%, but how hot does it have to get before the rocks on the planet release more carbon dioxide, which makes it hotter, which causes the rocks on the planet to release more carbon dioxide, which makes it hotter? That is something to seriously be concerned about. All right, let's move along here to a little bit more about Venus. We mentioned already it's Earth's twin. You can't see the surface because the clouds are so thick. There's a lot of plains. There's a lot of volcanic flows that cover over its surface. Venus has been resurfaced a number of times, so its surface doesn't look old like the moon's surface does. Here's a picture of Venus. Let's move on to Mars, one of the most exciting places in the solar system. One of the few places we have the possibility of making a colony. Is not going to be easy, but there's a small possibility we could pull this off. There's understanding of how we could make it work. It's got only about 1% the density of Earth, so that means a lot of things. First of all, it means that there's not much gravity compared to Earth. And because of that, Mars has actually lost its atmosphere. That's one of the reasons it's lost its atmosphere. There is some gas there, but not very much, because the sun has heated it up and it's been driven off. Now, one of the things that protects gas on our planet is our electromagnetic field that is generated by our liquid nickel and iron core down deep in the center of our Earth. That's part of kind of the structure of our planet. If a planet cools enough that doesn't exist anymore, it loses its magnetic field, and the magnetic field protects it from nasty solar radiation. So there's another problem on Mars. Not only does the solar radiation boil off the atmosphere, but the solar radiation is going to annihilate anything trying to live on its surface. So one of our ideas is, hey, can we dig a hole? Can we find an old cave on Mars? Can we build a colony in the cave? Can we build protective structures? Can we somehow create a magnetic field that might protect us? A lot of problems with Mars, but it's still probably the most habitable place aside from Earth. Be much easier to fix our planet than try and live somewhere else, right? So, as far as the atmosphere goes, there are big dust storms on Mars. It clouds the whole surface up at times, so we can't really see the surface. It's a big problem for our rovers getting covered in dust. But the atmosphere is so thin that if you were to stand in one of these storms, even though the wind is blowing very, very fast, it wouldn't feel like anything at all because there's just not many molecules that would be hitting your body. It would look like a really serious storm, but it wouldn't feel like much. Now, you wouldn't be able to see anything, so it would be a problem in that respect. Looking at the surface of Mars, it's old. It's heavily cratered. It was beat up early in the formation of the solar system. So we're looking at features that are from the early solar system. Earth, in comparison, has been resurfaced by plate tectonics many, many times. So our surface is very fresh, very new in comparison to that of Mars. Here's a picture of Mars. We've got the big valley there in the middle. And, of course, Olympus Mons with the giant volcanoes over there. Very, very interesting place. There is evidence, strong evidence of water on Mars' surface. We don't see flowing streams now, but there are definitely rounded pebbles. All the geological features we see here on Earth in terms of moving water exist on Mars. So we know for a fact that Mars had water. Where is it? Well, a lot of it was probably lost. Some of it's underground. It can occasionally seemingly migrate to the surface and make new features. So that's something we really want to discover. We want to dig. We want to find water, because if you can find water, there's that much of a greater potential for life, right? There's an old picture of Mars surface. We've got much better pictures now, right? Now we have the rovers. So moving on to the outer planets, we jumped over the asteroid belt, but Jupiter is gigantic. This gargantuan is 2.5 times greater than the mass of all of the other planets and moons combined. It is huge. It's the big dog. It's mostly hydrogen and helium, the same stuff as the sun. So had it gotten larger, by like a factor of like 6 times maybe, I think that's about right, it could have been a second star, but it would have had to have gotten considerably larger. Looking at Jupiter, the most noticeable feature is the Great Red Spot. It's huge. It's a giant storm on the surface, and it changes over time. We can watch it change real time. The clouds on the surface that we can see are some dark bands, some bright bands. They're moving in different directions. Some are rising, some are sinking. But that's what gives it its banded structure. Imagine a planet that's all atmosphere, that's all gas. Jupiter is so big that it's essentially its own little solar system. It's got a whole bunch of moons, like 28 discovered so far. It's like basically a miniature little solar system. And it also has rings. We didn't expect to find rings, but as we're finding now, the majority of the planets probably, some of them still do have rings, but they probably had rings as they formed. Earth more than likely had a ring system when it was forming. It seems to be a very common feature among the planets. Looking at Jupiter's largest moons, we've got Callisto, Ganymede, Europa, Io. These are some beautiful moons, and there's some very spectacular features on them. There's some very interesting things about them in terms of potential for life, and it would be some interesting stuff to go visit some of these moons. Moving on to Saturn, otherwise known as the jewel of our solar system. It's one of the most beautiful planets in our solar system, primarily because of those rings. We used to think that they were unique to Saturn, but now we know that other planets have rings as well. It's just that Saturn's are super noticeable and really pretty. It's a very active place, Saturn. It's similar in many ways to Jupiter, with a wind system, big storms, cyclones. There's lots of stuff going on in terms of the atmosphere of the planet. But remember, once again, it's a gas giant. You can't go to Saturn, Jupiter, those outer planets, and stand on them. You could fly a plane through them. They're gas. Picture of Saturn here. I think we mentioned most of this already, but it also has a moon system. So moons are otherwise known as satellites. They don't have to be man-made. 31 moons. Titan is among those, and it's even larger than Mercury. So these outer planets are like little miniature solar systems. Picture of Saturn's rings. Uranus, the sideways planet. So Uranus is tipped almost 90 degrees to its rotation, or its axis of rotation is tipped almost 90 degrees to its plane of the orbit. So all the other planets roughly go around the sun and rotate on their axis perpendicularly, if you can picture what I'm saying here, to their orbit around the sun. Uranus is tipped totally over and rotates on its side. So why in the heck did that happen? Nobody knows for certain, but more than likely, it was clobbered by something early on in this formation. Earth itself is tipped 23.5 degrees to the ecliptic, to its orbit. And we're pretty certain that the reason Earth is tipped like that is because when our moon formed, we got hit by something about the size of Mars. So it tipped us over, and then that's how we got our moon. It's also kind of convenient that we're 23.5 degrees because that gives us the seasons, and that's awfully nice. Nice to come out of winter once in a while. Here's a picture of Uranus. Neptune also has some very strong winds, right? 1,000 kilometers per hour. It is a very, very windy place in the solar system. Here's a picture of Neptune. And a real quick mention here of old Pluto. So Pluto, which is no longer considered a planet, and that's not necessarily a bad thing. It kind of had it coming, really, in terms of the planets. It never really fit in. It's outer. It's one of the out. It's one of the outer parts of our solar system, and its orbit's very eccentric. It's not very circular. Sometimes it even crosses between Neptune's path. It did not do a good job of cleaning up its neighborhood of debris. It doesn't fit with the other planets. It's very icy. It's not a gas giant, which is what all those outer planets are. It's got a moon, which is almost the same size as itself. So it's a kind of a strange place, and now we've relegated it to the realm of what we call dwarf planets. There's a whole bunch of these things that we've discovered, and we just keep finding more. They're hard to find because they don't emit any light, really, other than what's reflected from the sun, which is not much from way out there. But we find more and more of these things. So we're faced with kind of two options. Either we start adding loads more planets to our already numbered list, or we start making a new group. And Pluto falls squarely within that new group of these outer dwarf planets. Okay, let's take a look at some other random features of our solar system. Something that we call an asteroid is anything that's a small rocky body. Can be anywhere from a few hundred kilometers to less than a kilometer. These things lie, for the most part, between the Mars and Jupiter orbits. Okay, take usually about 3 to 6 years to go around the sun. Occasionally, yes, these could be disturbed by another passing asteroid or a comet, and that could take them on a trajectory that might come in and collide with Earth. So that is where some of these things come from. Okay, take a look at the asteroids here. Some of them have some very, very irregular orbits. Why do they do that? Well, they've been disturbed by other things, right? So they end up on a different path. And sometimes that crosses Earth or the other planets, and we have a collision. Comets are another thing we talk about. These things they're small, they're rocky, but they're also frozen gases. So they're like big dirty snowballs, you might think of them. They come from typically very far out in the solar system with really elongated orbits, and it can take a very long time for them to make one complete pass around the sun. Some of them have orbital paths that are so far, so distant, that it can take much longer than a human's lifetime to actually have it come around. So there's some comets that have come by that we will never see, but other generations will. The parts of a comet are distinct. The coma is the fuzzy gaseous component up by the head. Okay. There's a small glowing nucleus with a diameter of about only a few kilometers. It can sometimes be detected inside the coma, that is the actual thing. As the comet approaches the sun, some but not all of them will develop a tail that will extend for millions of kilometers. Now the tail is not pointing the direction the comet is moving. It actually points away from the sun, from the solar wind. So even though the comet might be moving parallel to the sun, there we go, there's a picture of that, the gases from that cloud of tail point away from the sun. So you see the orbit there, see the gases pointing away from the sun. Think of the sun as blowing the dust off the comet in a way. It's heating up the comet, and then the comet's off-gassing all that stuff. So comets come from far out in something that's known as the Kuiper belt. They're way out there. We also have comets that come from an area known as the Oort cloud, which have even bigger orbital periods. So the Oort cloud is kind of the spherical shell that surrounds the solar system. It's kind of one of the outer features of our solar system. Wouldn't be complete without a mention of Halley's Comet. This thing is famous. It's got a period of 76 years. I saw it when I was a kid. It was spectacular. It was very, very cool. It's not going to be back around again for quite some time. You guys should, I believe, have the opportunity to see it if you live long enough. Last couple of things here. Meteoroids, meteorites, meteors. There's a slight distinction. It's easy to confuse them. A meteoroid's a small, solid thing that's going through space, kind of like an asteroid, but smaller. A meteor is something that's going through our atmosphere and burning up. Most of these are what we call shooting stars. They're tiny, small, size of the grain of sand. They burn up. They look like a shooting star going across the sky. That's what they are. Meteorites are any of that stuff once it lands on Earth's surface. So if a meteor doesn't completely burn up, it could be a meteorite. Okay. Yeah, so a lot of our meteoroids, meteorites, meteors, they actually come from the remains of comets. So it's material that, as the comet passed by, has left in its wake, kind of sitting out there in space. And as the Earth goes around the sun, Earth passes through these belts of material at a pretty regularly repeating cycle, at least one that we can calculate, and we can know like when the next meteor showers are going to happen. So there we have it. It's the end of our talk for today. You guys have a good day.